time. I totally did start and I'm going backwards. All right, so number one, simple harmonic motion, the cause. So these equations up here kind of describe that cause, but really the cause goes to what we talked about for about 15, 20 minutes one day into about half the time the next day, and that is being able to talk about that Newton's second law. As a matter of fact, let's just push this over here. Kind of talking about the cause, going from Newton's second law into talking about acceleration, what effect acceleration has on velocity, what effect that, and whether or not position is different or not, and whether or not that fact should change things. For example, very quickly, I could be like, why does mass affect things for the spring system? Well, because more mass on it will increase the inertia right here. And in a weird sense, even though it has a different equilibrium, more mass does not increase the force on a spring system. Therefore, if that stays the same and that goes up, acceleration goes down. Acceleration going down means you have less velocity. Less velocity, if you are going through the same amount of displacement, which you are, because we're assuming equal amplitude on both sides, means smaller velocity, you should have a larger period, which is reflected in this equation by the fact that more mass means more period. Fair enough? That being said, I should also be able to give you this on a test at any point in time now, talking about factors. Like, according to this equation up here, if I double the mass, what effect should that have on period? What's that? Correct. The period should not go up by double because of the square root right there. Okay? It should go up by 1.41 or the root of 2 in that particular case. Does that make sense-ish? Just like if I gave you this equation, I said, hey, I double mass, what effect does that have on acceleration? Half, yes? Or if I said, of course, if I say that sentence, what am I telling you, assuming about absolutely everything else? Assuming you say it's constant, so let's do one more. If I said this guy, I double mass, what effect does it have on kinetic energy? Doubles it. I double speed, what effect does that have on kinetic energy? Quadruples it. Yeah, those powers can have a big effect on it. And remember that square root actually is a power. It's just a 1/2 power up there, which is why if I doubled mass, it would change by the square root of 2. What if I doubled k? How would you say that? You could actually just say reduce by square root of 2, okay? Or you could change by a factor of 1 over root 2. Would be another way to say that as well. Does that make sense-ish? Cool. Okay, so cause, and then the description of simple harmonic motion, of course, comes from this generic equation, which of course a lot of things can change in. The main things, of course, that could change is, of course, I could trade out x for y, and I could certainly change out cosine for any of the trig functions depending on the starting condition. Questions about that? Okay, number 2. The second part of the TIWKIIWY, waves and interactions. And as you see up there, reflection, interference, and standing waves. So kind of that whole conversation that we had yesterday. Now, I don't know, I told first hour, I don't know if I told you guys this at the beginning. I knew from the very beginning, obviously, we were going to have to go a little faster through this particular chapter. So I want to make sure and kind of somewhat, hopefully put you a little bit easy about the stuff tomorrow and say 2 things. One, it's not meant to be tricky on the multiple choice. It's a little bit more generic, a little bit more kind of towards the vocab, understanding kind of what these things are that we're talking about on the multiple choice, less kind of like, what's the in-depth if this perfectly changes here, and less more challenging multiple choice. It should be an easier multiple choice in general. 2, there are actually more multiple choice on this test than usual. There's about 16 multiple choice, and I did that mostly so that so I could make the problems a little bit easier. It could go a little bit faster. And 2, on top of that, I'm going to make therefore the multiple choice get a little bit less. Each one of them is not as individually as important. So if you do miss one, it doesn't have as big of an impact. Last thing is, I decided this yesterday because we're kind of running out of time. There will be reflection and interference stuff on there, very basic stuff, not super in depth. We can certainly talk about all those. But I did take off a couple of problems about standing waves because I would love at least another day to talk about them if I really wanted you to kind of truly get to the heart of it. Now, I mentioned this yesterday, and I'll say it again because some first hour people did it, and it really kind of did help them about standing waves. I'll talk just very quickly, and that is this. A standing wave is a very specific frequency that causes the incident wave, meaning the wave I put out, and the reflected wave to interfere at very specific spots. Okay? Meaning, in this particular case, if you look right there in the middle, this frequency is causing two waves, although you can't see it, you're just seeing the resulting waves. There is a wave going out, and there is a wave being reflected back, okay, that are in the middle, destructively interfering the whole time, okay? Kind of in this first fourth right here, constructively interfering, and in the last fourth over there, constructively interfering. Okay? Now, the best way to probably understand these, that I say it has to be a very specific frequency, and I think I mentioned this yesterday, but here it is again, is if you get the chance, come up here, make this wave, okay? Make a wave or very similar to, and then attempt to get to the next wave. Okay? Try to get to the next frequency of wave. If you don't quite understand that, you see how there's kind of like two packets out here? We talked a little bit about this yesterday, kind of sections, and we talked before that two packets make a full wavelength. Like this wavelength right here is 38 feet, the distance from the front of the room to the back of the room. Okay, but if I try to make the next one, I'm just going to make, instead of two packets, I'm going to try to make three packets. And what you'll notice while you're doing it, and you can watch my hand while I'm attempting this. I missed it. It's actively fighting me until I get there. Now, why is it once I get here that it doesn't actively fight me? Well, because my hand is putting out a frequency that is going out and coming back, and that frequency is now pushing my hand up and down at the exact same frequency that it's supposed to be putting out. So my hand is causing an incident wave, sure, to be going out, but there is another wave coming back that is pushing my hand up and down at the exact same frequency that it's supposed to be pushing it up and down. Whereas when I'm in the middle, like let me go back to 2. Now you can see it's like actively fighting me. There. When the frequency is wrong, it's pushing my hand up when it's not supposed to, down when it's not supposed to, so it feels like it's fighting me until I get to the exact right standing wave in which the perfect frequency is going out and then coming back here, and that frequency is pushing my hand up and down at the exact same frequency that my hand is pushing up and down, which settles in very, very nicely to that particular spot. Yes?
That's one more question.
Sure.
That's like which lengths or which wavelengths can make a standing wave?
Absolutely, yeah. Sure, absolutely. Okay, so there was two things I wanted to hit today before we actually kind of got into any individual questions, and they were both homework questions. Let me actually tackle the first one first, and then I will tackle that one next. Okay, and the answer is actually relatively simple. Okay, so the first one that I wanted to address is the two graphs. Like, how do you graph a standing wave? Well, ultimately, there has to be multiple graphs because you really can't get away. You can't do this you can't graph this in two-dimensional space, and here's the reason why. The first graph that you're probably the most used to would be this one. I'm going to say y with respect to t. And this guy is at a very specific position. So I'm going to pick a spot. I'm going to pick a spot right here. So I'm just going to, this guy right here. So this black area right there. Okay, so just watch it, okay? And once I get it going here, once I get a standing wave, awesome. Guess how that guy is moving up and down? Simple harmonic motion. So guess what its equation is going to be? Just simple harmonic motion, correct. It is literally just a times the cosine of omega t. Now we don't need the equation. What we need
and it can be
is the graph.
T if it's at the 0, right?
Oh, yes, I'll get to that and just say, yeah, what trig function we use just depends on where you want to start it, right? Like if I go back here, okay, if you want to start this trig function when it's at the top, if you want to look at it when it starts at the top, great. Guess which trig function you should use? Cosine. Whereas an interesting fact, if we were to go then 3/4 down the line, when this guy is up, the other one over there is down. So what should we use in that case? We would use negative cosine to describe it because it's at a different starting location. Okay? Whereas, and I think you were just saying this, what if it was at equilibrium and headed down? What trig function should you use? Negative sign. Correct. Negative sign in that particular case. So I will do it from the very top. So I'm just going to say cosine. Now, can I continue to draw these? 100%. Well, I did it like, probably 30, 40 times since then. I'm not going to redraw this 30, 40 times. So please understand that it does technically continue forever. Now, this axis, of course, is t. As time continues, that spot's going to go down and up and down and up and down and up and on forever. But one particular key spot of that is one full cycle. What is one full cycle on that graph? A little period, yes, capital T. There you go. Yeah. And so technically, if you'd like, we can come over here and call that 2t, and so on and so forth. But a lot of times you only have to draw one function. Now, the other graph that you're a little bit less used to, but is arguably sort of even easier, is y with respect to x. Okay? Why is that easier? Well, let me share with you a graph of y with respect to x and z. Okay? It looks very complicated to write it mathematically. That graph is your vision. Keyser is over there, meaning he is so much x away from me, he is that much y, and so much z. As I look around, this is literally, y versus x is literally a snapshot picture. So where this was at a very specific position, this would be at a very specific time. So in other words, imagine that you just took a picture, and that's what you're graphing. So if I come back to this, to mirror this one on the bottom, we'll start the situation. We will start it, we'll just use this guy right here, okay? And start it when that guy that we were talking about is on top. In which case the graph would look like that. Now, there is some uniqueness to this. I cannot continue this one like I could continue that one. How come? Because that barrier there, right? It actually stopped because of it. Now, I could start to draw this. I could draw this guy. And then it would be this guy, even though he's kind of along those lines. And then this guy. And then, for sake of Brianna, no jokes. There we are. Okay, right there. When would that occur? At what time would that occur? Period over 2. This guy right here, both occurred at 4 3/4, and obviously how much time is going to take for that to repeat itself? 1 period by definition. Now, where we highlighted this guy, 1 cycle for that is period. What is 1 cycle for this guy? The distance that it takes for 1 cycle is called wavelength. Now, like I said, I could have you draw a different picture. I could have you say, all right, instead of this one, where I did like 2 packets, I could have you get to, come on, there it is. I could have you draw 3 packets in this particular case, in which case, of course, it would look like this. And if I really wanted to. Okay? And this is y with respect to x. It's sort of also with respect to t when I draw these dotted lines up here, because you can see kind of how they change over time. But if I call this whole distance, L, I don't like that at all. Sure, close enough. Okay, if I call this whole distance L, what would wavelength be? Not half.
Oh,
2/3 L, or 2L over 3.
And what if the dotted lines represent again?
At another time.
Oh.
So this would be like 1/8 through the cycle. This represents a quarter through the cycle. Then 3/8, then 1/2. Kind of just I'm drawing it in time, like it's going up and down. That's
Y
what I'm trying to
versus
go.
T is one wave and how it moves, and that's a snapshot of a wave.
Correct. I mean, and like I said, the dotted lines sort of make this y versus x sub t because you're kind of looking at it in time as well, but you don't actually see it with respect to time. So yeah, this is a y versus x graph. And to be fair, I'm trying to help you to see this. When you draw these, you do not have to draw the dotted lines unless they do in fact help you. You can just draw.
What are the dotted lines?
The dotted lines just represent that at another time.
Oh.
So like, where is this guy going to go over time? Well, the first place it's going to go is here, right? You can see that at a certain point in time. Let's see if I got this here. See how like if you could take a snapshot of when it's actually like flat,
Yeah.
right? Not very long, so it's kind of hard to imagine. And then at 1/2 the period later, it's down here. That's what the dotted line represents. It's just it's kind of showing how it changes in time. Oh, dotted lines are fickle for the undo button. All right. Now, that perfect, yes.
Let me ask, what do you label the y-axis for pulse waves? It said on the question of label the axis.
Well, is it with time or with x?
Uh,
When I did these yesterday, I drew a string, okay? That is technically both a picture of the string and a graph of the y of it with respect to.
right y of x, not right like.
Yeah.
Height.
Y of x is like way more complicated than people draw. Let me show you a y of x picture of a smiley face. Admittedly, it's not a function, but it is a y versus x graph of a picture of a smiley face. As the x changes, we get various values of y occurring at particular locations. A picture is a y versus x graph. So obviously, you're not going to do anything complicated with that. But this is to say, when you draw a picture of a situation, okay, like watch, here is a person running. That is a y of x graph of the person running. Yeah, look at that.
And then
And he's sad about it. All right. He's running. All right, moving on. So now, that last conversation right over here, where I talked about this versus the 2L over thirds, gets perfectly into the question that was asked, which ones are available? And to help with that, let's just do something very, very simple, okay? This, right here, is the lowest possible frequency of a standing wave I can make. And the question becomes why? Well, let me ask you a different question, okay? How many nodes are in this? 2. What are they? The barriers, the boundaries. Why do they have to be nodes? No, that's not it. It is it, and it's also not it. What is a node?
where it's
Where it's
always
perfectly destructive. And what happens at a fixed boundary? It reflects, which means the wave coming in always has an equal and opposite wave coming out on the opposite side. So what will always occur here? A node. Now I specify this because away from the fixed point thing, because I would love to just be like, yeah, it is tied down, obviously. Because if you do continue forth in the physics of sound, here I have 2 free boundaries on the opposite side. Guess what always occurs here? Antinodes. Because when a sound hits this barrier here, what will occur? What occurred at a fixed boundary? Reflection and inversion. What occurs at a free boundary? Reflection and no inversion. So a wave is going in with this much amplitude. And a wave is coming out with this much amplitude. So what will always occur at free boundaries? Antinodes. Constructive interference will always occur. We're not going to worry about this, okay? That was kind of just for people continuing forward. If you ever, and then you get into really interesting things when you start to deal with things like the kalimba, or if I were to like put a barrier right here, okay? What happens if I put a barrier right here and start hitting this thing? Actually, here, go ahead and hit it. Hit it again. I just changed the frequency by changing the barrier. Why? Well, because if I make a fixed point right down here, a node has to occur here. And what has to occur here? An antinode, which kind of changes things. Now, how does it change things? Well, forget everything I just did. Let's just talk about the string. That's all we're going to worry about, is talking about the string. And here's what you need to worry about with the string. What must occur here and here? A node. So this is the first possible shape that I can make. Yes? And if this is L, okay, like pick a number, I don't care. Let's say a meter for the sake of simplicity and numbers here. What is the wavelength of that?
562.
Try again. What is the wavelength of that? 2L. Or 2 meters. Why is it 2L and not just L? That's not a full cycle, that is a half cycle. Now, the simplicity with which this occurs, don't make it more complicated than it needs to be. A node has to go here. A node has to go there. What is my next possible option to evenly put this? Oh, well, a node would have to go in the middle next, right? That's the next possible option. Now, if I draw that, so there you go. So what is the wavelength of that guy? L. So again, if L is 1, our options are, sorry, the standing waves of guitars, that was an accident. Okay, our standing waves are 2 meters and 1 meter. So can I have a wavelength of 3 meters? No. Can I have a wavelength of 1.5 meters? No, physically it's just not possible. Now let's look at our next couple options, and I think you'll get a general gist. A node has to go here. A node has to go here. Now notice here I had no nodes in the middle. Now I have 1. Guess how many I'm going to have now? 2. And I'm going to need those to be relatively evenly split up. So my next possible option is, what is that wavelength? 2L over 3, or 0.67 meters. Yes? If you're assuming L is 1. Let's go one last one. Guess how many nodes are going to be in the middle? 3. Evenly splitting those up. I'll put 1 in the middle. I'll put 1 here. I'll put 1 here. We have shown absolutely all of these on the spring. Kind of 1 packet, 2 packets, 3 packets, 4 packets, but again, the packets are kind of a little bit misleading because a single packet is not a wavelength, right? Because you've got to remember it's bouncing up and down at the same time. What's the wavelength of this guy? 1/2 L is correct, or 2L over 4. Now, the reason why I'm drawing them in that particular way and not reduced is pointing this out. Notice how the wavelength, let's just do this guy real quick, 2L over 2. So, compared to the original wavelength, what happened to the wavelength here? It's, and if this equation right here says they are invertedly related, if I cut the wavelength in half, what happens to this frequency relative to, we'll call this the original frequency? It doubles. How does that guy compare to the original frequency? Well, it's 1/3 of the original wavelength, so that means the frequency is 3 times the original frequency. And finally, you get the idea. What we are doing here, and I'm not going to go too much far into this because I do want to potentially give more opportunity for questions, but I do know this is going to be interesting to some people. These are the harmonics. Okay, if you've ever heard of harmonics of a particular instrument, various instruments will play various amounts of each harmonic, which basically gets into why they sound differently. This is why I can play a piano, a drum, a saxophone, and the trumpet all at middle C, and they all sound this. They are the same frequency, but they sound entirely different because they play different values of these relative harmonics. Also, just one last thing, we're not going to get into the why of it all right now, but this is known as the fundamental frequency, or simply put, it's the lowest frequency. The lowest frequency is the note that is always played by that particular instrument, which is why we can actually look, as I've shown a couple times, at the lengths of things to decide what note is going to be played. If it's going to be higher pitched or lower pitched. If I have this setup. Questions on how you can determine? Honestly, if you didn't get a lot of that conversation, we're at the end of the year. I want to make space for you here to understand this. If you just have that slide right there, literally copied into your notes, you get, and you know the length of the thing, you can use that to be. These are the lengths. These are the wavelengths that are possible, and there you go. What are you taking a picture for? Draw it. Just write it down. It doesn't take that long. Yes.
You said that I'm making sure there's always an anti-node when there's an open end.
Correct. Yes. Yep. When there's an open end. Yeah, and I'm not going to get too much into that on the test either. Yeah, Jake.
What is a wavelength?
A wavelength is the physical space that it takes to repeat a cycle. So it is the measurement of length that it takes to complete a cycle. So I will draw it for each of these. Oops. The wavelength is that distance. So right here, for this spring, when I do this, I think we measured that the length of the room is about 38 feet, right? Something like that. So the wavelength is 38 feet. Okay? Or in this particular case, hold on, 3876. What's 2/3 of 76? Someone punch it in. I mean, I guess I could just count it as well.
50.7.
What's that? Good. No, that's not right. 2/3? Hold on. I screwed this up. I'm sorry. My apologies. 2/3 of 38. I can do that one in my head. 13.26. It's like 27, 28.
25.3.
Okay. Here we go. 25.3, 26-ish feet. Okay. So here you can see that the wavelength is 26 feet. Okay. Or here. Okay. Right here, about half the room, so 19 feet. The wavelength is the distance for one cycle to repeat itself in space. The reason why it's particularly helpful is that a period is how much time it takes for a cycle to complete, right? The wavelength is how far that a cycle goes when it's in physical space. So here's a good note. Okay, if I am playing. So generally speaking, the speed of sound is about 343. Yes. Okay. And I think we looked it up yesterday. I think A is about 343-ish. It's a little higher. It's not perfect. Don't quote me on this, but I think it's like 343. So if you were dealing with sound, that's 343 and that's 343. It would be kind of hard to see, but the wavelength of sound is 1 meter in that case, meaning the distance that we talked about yesterday from compression to rarefaction to compression is 1 meter. Yes?
So on constructive interferences, I know like they come together to like make like a big thing. So like with the amplitudes, like would you add the amplitudes?
Yeah. Yeah, just simply add. Yeah. So what I showed yesterday, and I realized I didn't do a great job of, is like for like two waves hitting each other that are more complicated, you get both. You don't just get one or the other. It's not like you look at a situation like this is constructive interference. Like if I drew this wave, and then I came along and I drew, say, like this wave. Okay, from here to here-ish, that would be destructive interference because they're on opposite sides. From here to here, that would be constructive interference. So you get both at the same time.
And then the other part of my question, so when you have a destructive interference, in order to have no sound at all, they have to be the exact same.
Perfectly match on opposite sides, yes.
And then so
Complete
like,
destructive interference.
Okay.
Yeah, so like technically, if I'm standing up here and I am playing it and I were to like just hit a note, okay, and say Keezer's like, nah, Smano's not talking today, right? And so he decides to play the exact same note. It would be very, very challenging for him to pull off. But if he could pull off the exact same note, 180 degrees out of phase. Now we're talking, if I'm playing middle C, that's 256 times a second. You'll remember that the period is like 3 milliseconds in that, right? So half the period is like 1.5 milliseconds. So he would have to nail the exact right time that he starts that so that it's off. But if I play A and he plays A just a little bit out of phase, then technically you should see both of us say nothing. Now, obviously, you know that's not very easy to do because you have never been seeing somebody talk up here and somebody in the room starting like, I'm going to challenge them, because absolutely teenagers would do this if they could, and to be kind of the anti of the anti-Spano, right? Anyway, and you talk at the exact same time, and then now I would be talking, of course, in that particular instance, but since someone was inverting that particular, so the other thing that you have to remember is that sound, the wave that is hitting your ear and the wave that is hitting somebody else's ear are not the same distance. So you don't hear them at the same time, and you don't hear them at the same amplitude. So Keezer, even if he did it perfectly, let's say I'm going to stand roughly how far Keezer is sitting from Chloe right now, even if he did it perfectly, it might perfectly balance out so it's quiet for Chloe, but does that automatically mean it's quiet for the rest of you? No, absolutely not, because we are getting different distances to you so that mine when it hits this group over here could be high, and Keezer's could also be high, and so they actually build instead of canceling, and also normal tone of voice is much, much more normal conversation like I'm talking right now. I am varying my pitch, I am varying my inflection, I am varying the complicated nature of that thing to create anything that would be the opposite of that would be practice. I mean, I showed you yesterday that noise canceling headphones don't come anywhere near to doing the exact opposite, and we consider that canceling. So, anyway, other questions? Yes.
So, could you have, like, what's the limit to the amount of nodes you can have in between two, as long as they're evenly spaced?
None. There are technically harmonics that are you could head towards infinity. It would be one thing you'll notice about them though. Okay, here's the thing. Here's the inherent thing based on the concept. Okay, notice when I do this. Okay, I'm not changing the amplitude I put in. Notice the amplitude that's coming out. Okay, now notice what happens when I increase the frequency. Hold on, I gotta get there. Now, is my hand playing a different amplitude? What inherently happened to the size of all of the amplitudes? They're shorter. Which means in terms of sound, they are inherently quieter, which you know this to be the case. Are higher pitched things inherently quieter? Yes. So, to get to the particular spot, like what is the limit? Well, technically it's at infinite, but let's say I just pick a high number. Let's say I have 30 nodes between them. Like imagine I've got 30 nodes on here. Are we going to have a high amplitude here? So in terms of like a musical instrument, even if it plays the 30th harmonic, is that going to have a huge impact on the sound whatsoever, whether it's there or not? No. So there gets to a spot in, let's say, physics/engineering, when we're looking at these things where we can go like, yeah, past 10. Let's really not worry about it, because it's going to have, like less than like a 1% impact on the overall sound of that.
So for like number 5 on 13.4, whenever I asked like What was the question?
I don't know. You brought it up.
Between the 2 meters?
Oh,
Something like that.
The number is like 5.
It was something, it asked you about like how many of something you could fit into the 2 meter restraint.
Yeah,
So excuse me, the 3 wavelengths that produce standing waves, name at least one wavelength that would not produce a standing wave pattern. I'm confused by your question. It's just, it talks in the question about the first 3. So the first 3 I'll tell you right now are 4 and 2 and 1.67. I have those memorized in my head, but those were 2L, L, and 2L over 3. Right? So, other question?
For number 4,
Yes, no.
like the antinodes, is it 3 or is it 6?
3. Each of these packets, this area, this position is considered an antinode.
Oh.
Yeah. Yep. And what'd you get for nodes it has?
4.
Yeah. Yes.
So can we go over just like the different types of waves?
Sure. Pulse, transverse. Okay. Single disturbance means pulse. Okay. Transverse means it's moving perpendicular to the medium. So you kind of got to do kind of this in your head / draw a picture. The medium's going this way, right? So let's give it an axis so we make it. So this is the Z. Yes. So I regularly do this just so that all of you can see and it's not a problem, right? That is transverse, but also this is transverse, right? It's moving in the Y, like I did to begin with, and it's going there, that's perpendicular. But it's moving in the X, that's also perpendicular. Also, technically, that is transverse, okay? This is a longitudinal pulse wave. Longitudinal is one in which the medium moves parallel to the wave. So the wave's going back and forth, and the medium's going back and forth like this. That's why sound is considered a longitudinal wave, because as I talk to you right now, the medium is traveling towards you, and the air molecules in between are going the exact same direction. You'll remember that the picture that I showed yesterday demonstrates that as well. Maybe. Open. What are you doing with your life, Spainhour? Make better choices. You can see in this picture right here that as the wave moves to the right, if you look at all of these individual particles, they are going this. Now, I also bring up this because this is a longitudinal periodic wave. Why? Because you'll notice this diaphragm-esque thing over here, vibrating back and forth, creating a continuous pattern that's considered periodic. Okay, that's periodic pulse. Periodic longitudinal, and then transverse longitudinal is what we've been doing a ton in here. Okay, your periodic waves do not have to, but oftentimes are standing waves as well. Okay, a standing wave is a periodic wave in which the frequency matches perfectly. So blah blah blah. We've already had that conversation, but those are your different types of waves. Yes.
So like when it's talking about transverse and longitudinal, it says like it moves in the same direction as the medium. But I thought the medium stayed still. Like the energy moves in the medium.
Well, okay, so but like look here. I mean, so the net movement is 0. Okay, are we saying that this guy is not moving as the wave comes by? No. How's it moving? Okay. Well, what's its net movement? In terms of transverse, no. In longitudinal, yes it is. Here, I'll show you. I will now create a longitudinal standing wave. Okay, now that one maybe not as easy to see, so let me increase the frequency. Look at that node right there in the middle. Is that middle guy moving very much? No. What is moving? Now notice how much I'm moving over here, maybe like 4 or 5 centimeters. Look at that little guy go really strong right there. What's that? An antinode. So, are they moving back and forth this way? Yes.
They're moving like it always describes it as like moving perpendicular to the movement of the medium, moving like parallel. So I don't get what the movement of the medium is. that's moving from the medium to.
I'm confused by your question.
In a
So the
transition-
medium here is the spring.
Yeah, but the medium. Does this mean like the direction the medium goes in, even though the medium itself isn't? Like even though. It's not
Yeah. So like if you took the medium, okay, I think I get where you're at. If you took the medium and you like cut a section of it, like just this piece right here, which way is this moving? Like right here. No, this guy's moving up and down as the wave moves back and forth this way, so it's transverse. Whereas in
going up
this
and down,
particular,
the wave is still going.
yes, yes, and that longitudinal wave I just made a second ago, you saw this guy bouncing back and forth this way, and like I said, standing waves are so weird to get used to. Hello? Yes. I do. Sure. Sure, can do. Okay. Jackson, please stop by the library on your way to third hour. They'll write you a pass. Cool. All right. Other questions? How are we feeling about the test tomorrow, 0 to 5?
I feel good for tomorrow.
No. Okay. Other questions or no?
Is the red dot?
What's that now?
The red dot that you put up there.
Is what?
What
Yeah.
is it? Is it
It's only to highlight so that I can point out a particular one. So like you can watch that the red dot does not actually go anywhere.
Yeah.
That thus kind of talking about the wave properties. That it is not, even though like it's very obvious that this is moving, right? If you look at any particular one dot, if you track one dot, the dot is actually not moving through the system. It is the energy that is moving. So it's just highlighting one particular guy. That's all it's doing. All right. Oh, I wanted to show this because I think it's just kind of cool. This is just a video. Obviously, this is computer animation I'm about to show, but it's not a real. I don't want you to think that I think it's real. Where's it go? There it is. But this gives a indication. I said the other day, is an ocean wave actually longitudinal or transverse? And the answer is both. Because actually, if you don't worry about that guy. Where did you go? I don't want that one up there. I need that. There we go. Okay. So, actually, ocean water waves actually curl. They go in a circle. Water actually. If you are at raging rivers or anything of the like this summer, what you'll notice if you are in the wave pool is when you are at the top, the wave is coming by. It'll look like this. When you're at the top, the wave will be pushing you that way. When you're on the side, the wave will be pushing you up. When you're on the back side, it'll be pushing you down. And if you're in the trough, it'll actually be pushing you that way. And that is because water actually moves in a circle. So if the wave is going this way, is it longitudinal or transverse? Well, when you're on the top, it would be longitudinal. And when you're on the sides, it's technically transverse. So it's sort of both. Also, when Spainhour speaks, is Spainhour talking in a longitude? So they're just general definitions. They're not perfect. But is he speaking with a pulse wave or a periodic wave? If he just says, boop, well, let me kind of draw a generic, definitely not accurate. There's Spainhour saying boop. Is that a pulse or is that periodic? Both. It is a packet of information, although within that packet of information, and I did not draw it nearly as many times as would actually happen, it goes up and down somewhere in the hundreds or 200 times, so it gets a little bit icky as far as that's concerned. Oh, here's another great video. Here's a perfect demonstration of constructive waves. Where'd it go? Hold on. Let's close out. When a water wave comes up and hits any sort of barrier, it is going to hit a boundary. Okay, water ideally when it hits that boundary, they use friction to diminish it as much as possible, but they don't always do it perfectly. So If water comes in at a constructive and then goes out with another constructive wave, you get some crappy situations. Where did it go? Come on. Are you going to do it or no? Do the thing. There it is. Don't be in the water at that time when you get constructive waves. Constructive interference, ladies and gentlemen. One last video in case anybody cares. Have you guys seen that you can actually take a microphone and by playing the exact right frequency, you can break it? You know what I'm talking about? Okay, it is very cool. This is how you pull it off. If you want to break, where to go? Hold on, I have it. Where to go? Okay, this is how you break a wine glass using a speaker system. It's not that hard. I don't understand why people have any issue with it whatsoever.
Did you stop the drinks being over?
No, I should probably stop.
Yeah.
No, take a very long